Hi guys, today we're going to talk about generalized SRv6 or G-SRv6 for short. In SRv6, a segment ID is a 128-bit IPv6 address associated with a segment. As such, SRv6 supports to carry a SID list with multiple SIDs in the SRH to instruct packet forwarding, and this is the basic principle of SRv6. Currently, in most scenarios, SRv6 is mainly best effort traffic without SRH, or TE traffic with less than 5 Cs. This means that the SRv6 header overhead is under control and acceptable. However, in scenarios where the number of Cs exceeds 5, such as TE or SFC scenarios, the SRv6 header overhead may be high. For example, if a SRv6 packet with 10 Cs, the following problems may occur. Low packet transmission efficiency. So the too big overhead will affect the transmission efficiency of small packets. Reduce hardware forwarding performance. If the SID list contains a large number of Cs, the size of C stack may exceed the parsing window size of chipset, meaning that the hardware must perform a recycle, which will affect the forwarding performance. So to address this issue, generalized SRv6 is proposed. In an SRv6 domain, Cs are allocated from an address block, we call it as C space. So they have the same prefix. For this reason, one C list may carry multiple common prefixes and other identical information, meaning that the compression is possible. For example, the prefix a:/48 is used as a seed space in an SRv6 domain, and the total length of the node ID and function ID fields is 32 bits, and the argument and padding fields occupy the remaining 32 bits, which are all set to 0. So for Cs in the seed list, the first 48 bits and the last 32 bits are all redundant, while only the 32 bits node ID and function ID fields are variable. In this way, we can avoid to carry multiple, redundant information in seed list to reduce the overhead of SRv6 packet. So this is the basic principle of SRv6 header compression. So the main idea of G-SRv6 is to delete the redundant information, such as the common prefix from the C list, and carry only the variable information like node ID and function ID, so thereby achieving packet header compression. The variable part is called a compressed SID, C-SID, or generalized SID, G-SID. To better understand G-SRv6, we define G-SIDs, which can be a single 16-bit or 32-bit C-SID, or a single 128-bit SRv6 SID. We also define a G-SID container, which is a 128-bit space that the segment left field points to in an SRH. So the G-SID container supports to carry multiple C-SID or one single 128-bit SRv6 SID in it. So in G-SRv6, different types of G-SID can be encoded into a single SRH. To indicate that the next SID is a C-SID, we need to define a new flavor. We call it as continuation of compression flavor. And it is also called replace C-SID flavor, defined in SRv6 compression draft, which has been adopted by IETF Spring Working Group. When processing a SID with CLC flavor, a node will use the next C-SID in the SID list to update the C-SID in the destination address field instead of updating the 128 bits in the DA as the normal SRv6 processing. So in order to locate a C-SID in the SID list, we need to define a new term called SID index to identify the location of the C-SID in the G-SID container. The SI field occupies the least significant bits of the arguments field in a SID. Similar to locating a SID through the SL field, we can locate a SID through the SL and SI fields. The processing of CC-flavored SID is very simple. When a node receives a SID with a COC flavor, it checks the SI value in the destination address. So if the SI value is greater than 0, it means that there are some CCs in the G-SID container to be visited. So in this case, the SI value is decremented by 1 to point to the next C-SID. And then it will be updated to the DA with this C-SID and then forward the packet. If the SI value is 0, it means that all C-SID in the G-SID container have been used. So we need to get the next C-SID in the next G-SID container. In this case, the SL is decremented by 1, point to the next G-SID container. In addition, the SI field is set to 3 or 7 according to the length of C-SID, so that we can find out the first C-SID in the next G-SID container. So after locating a G-SID or C-SID in the SIH, we can update the C-SID to the IPv6 destination address, and then we can forward the packets based on the updated destination address. Here, I will use a simple example to describe how G-SRv6 works in forwarding. Assuming that a packet needs to be forwarded from node 1 to node 9, and they support G-SRv6. The common prefix of SID is a://64, and the node ID and function ID fields are both 16 bits long, but actually it can be like 20 bits and 12 bits. It's up to you. So the argument field is 32 bits long and all set to zeros. As such, the SIDs from a:1:1:1 to until a:8:1:1 are all end-SID with COC flavors. And a:9:2 is the normal SRv6 end-SID without the COC flavor. So this figure shows the encoding format of the SID list in the SIH. In reduced mode, the first SID a:1:1 is not encoded in the SID list, and it will appear only in the DA. Therefore, the SL field can be set to 2, and the SI field set to 0. When the packet is forwarded from the node 0 to node 1, no one detects that the a:1:1 in the DA is a COC flavored and SID allocated by itself, and then it checks the SI value. Because the SI value is 0 now, so the N1 decrements the SL value to 1 and set the SI value to 3, and locates the next CC to /1. And then the node 1 updates DA to be like a:2:1:3 and forward the packets based on the updated DA to the next hop's node 2. So after receiving the data packet, node 2 process the COC flavor and SID in the similar way. Because the SI value is greater than 0 now, the N2 decrements the SI value to 2 and locates the next CC 3:1, and then it updated CC to the DA and then forward the packet to the next hop, node 3. This processing repeats again and again until the packet is forwarded to the node A. So when the packet is forwarded from node 8 to node 9, the node 9 detects that the DA is a:9:2:, which is a normal end SID allocated by itself. So the N9, the node 9 will process this SID as a normal SRv6 processing and end the forwarding. So now we have a basic understanding of G-SRv6, and we can see that the G-SRv6 has multiple technical advantages. First of all, G-SRv6 is compatible with SRv6. It supports smooth upgrade from SRv6 to G-SRv6, and it does not change the SIH encapsulation format at all. Secondly, GSRv6 supports efficient compression and large-scale network deployment. Using 32-bit CCOG SID, the GSRv6 supports large-scale network deployment and reduces SRv6 SID least overhead by up to 75%, which keeps the best balance of scalability, efficiency, compatibility, and flexibility. And if you're using 16-bit GSID, then the compression can be better. The third one is that GSRv6 supports flexible address planning, consuming fewer addresses. It can provide stable compression regardless of the prefix type and length, and it allows operators to plan the GSRv6 seed space based on their own IPv6 address without any specific or special requirement. And also we can avoid readdressing in the future. Since GSRv6 will not introduce new extra rules, security policies, and even new address comparing to SRv6, so we can smoothly upgrade the live network even from SRv6 to GSRv6. With the best balance of scalability, efficiency, compatibility, and flexibility, GSRv6 can help you to enjoy the benefits of network programming with much lower cost for today and the future. Thank you.